Hi guys, welcome back to Calculus. This is Mr. Robeson. Today we are going to take a look at finding the area under some sort of a function or a graph, and we're going to tie that together eventually with integrations or integrals. All right, so this might be new notation for some of you. This symbol here is the summation notation. So this sigma is what we call it. So this is the letter sigma. It's a Greek letter, it's capital sigma. All right, it means we're adding up whatever is in here over and over and over again from I equals 0 to I equals n. All right, so this I changes. So we plug in 0, so a sub 0, plus we plug in 1, a sub 1, plug in 2, plug in 3, plug in 4, all the way down until we get to this n up here. This is our upper bound, and this is our start. All right, so if we have some sort of constant being multiplied by this a sub k, this constant will be in every single one of these terms. It'd be k here, a k here, a k here, a k here. So in other words, we could factor out this constant outside of the summation. All right, so it doesn't matter what the bounds are. It doesn't matter if we're going from 1 to 100 or 1 to 5 or 0 to 100, whatever. This k can come out front. All right, so let's just practice a little bit of summation here. So if we want to go from 0 to 4, we've got I plus 1 quantity squared, so we would plug in 0, 0 plus 1 squared. And then we would plug in 1, 1 plus 1 squared. Then we plug in 2, and we keep going until we get to 4. So we got 3 plus 1 squared, and running out of room here, 4 plus 1 squared. And then we're just adding all this up. So this is 1 squared, 2 squared, 3 squared, 4 squared, and this last one here is 5 squared. So we get 1 plus 4 plus 9 plus 16 plus 25. So that's 55, I think. Somebody can check my math. All right, so the summation of this guy is just 55. All right, if we try this one, so we could leave the 3 in, or it's a constant, we could take the 3 out front. And we could say this is 3 times, and then we're going to plug in 1 to 5. So 1, 2, 3, 4, 5, like that. So if we add up all the numbers from 1 to 5, I think that's 15. So we get 3 times 15, which gives us 45. So this is how summations work. All right, so now we're going to try and find the area under a curve. So use 5 rectangles to approximate the area of the region between the curve f of x equals negative x squared plus 5, the x-axis, x equals 0, and x equals 2. And we're going to do it 2 different ways. We're going to use right-hand rectangles and left-hand rectangles. So the first thing I'm going to do is I'm going to draw just a little sketch of this curve here. It doesn't have to be perfect. So let's see, at 2, so at 0 we'd be at 5. So maybe this is 5 up here. It's a parabola opening down. It looks something maybe like that. It does keep going down like that. And this is y equals negative x squared plus 5. We're going from 0 to 2, so x equals 0 is right here. Maybe this is 1. Maybe this is 2. And by the time we hit 3, we should be below. So yeah, that'll work. That's fine. All right, now we want to use 5 rectangles. That's kind of a weird thing to do. Why would we want to break this up into rectangles? Well, we want the area of this section here. That's what we're trying to find, the area of this section here. All right, so one way to do that would be if we could use like the area of just shapes that could fill in this section. And the easiest shape to use is a rectangle, because the area of a rectangle is just length times width, or base times height if we're going up and down. So if we're going from 0 to 2, we want to know how wide is each rectangle going to be? What's the width of each of these rectangles going to be? Well, what we do is we subtract. 2 minus 0 is 2, and then we divide it into those 5 rectangles we want to make. So each one of them is going to be 2/5, or 0.4. So we got one rectangle here, one here, maybe one there, and one there. So this would be 0.4, 0.8, then 1.2, 1.6, and then 2. Now it says we want to make rectangles using the right end. So we got a rectangle going from here to here, and we want to use the right side for the height. So we use the right end up. There's our curve. We go over. We miss a little bit, but it's still pretty close. 0.8, we go up, hit the curve, go over. 1.2, we go up, we hit the curve, we go over. 1.6, we go up, we hit the curve, we go over. And at 2, we go up, we hit the curve and go over. So it looks like this will be an underestimate. All right, because there's this little area here in each one of these that we are going to miss. So this is an underestimate. All right, so now if we want to find these areas, let's see, each one of these rectangles has a width of 0.4. So this first one, it's going to have a height here. So we're going to plug in 0.4 into our function. So it'd be f of 0.4 times the width of 0.4. The next one's going to be f of 0.8 times the width of 0.4. The next one's going to be f of 1.2 times the width of 0.4. The next one's going to be f of 1.6 times the width of 0.4. And the last one's going to be f of 2 times the width of 0.4. So if you notice, we're adding up a lot of the same thing over and over and over again. This is where the summation stuff is coming in. So we could write this as the summation from 1 to, let's see, we're doing 1, 2, 3, 4, 5 rectangles. So from 1 to 5 of f of 0.4, 0.8, 1.2. Well, that's just 0.4 times I. So 0.4 times I times each one of them times this 0.4. All right, so that's what we're doing. We could write this as a summation. All right, I'm not going to work that out. We could work that out. I mean, you could type this into your calculator, do 0.4 squared, negative, subtract it from 5, and so on. You'd get some sort of a decimal answer, but definitely you can work this out. All right, on the other side, we're going to do the same thing, but left end rectangle. So it's going to be a similar picture here. So let's see if I can draw it almost the same. Let's see, we should be up here at 5 and coming down. Let's see, we got 1 here. Make it a little wider this time. 2 here. All right, we're still counting by 0.4. We're still doing 2 minus 0 divided by 5. So each one is 0.4, has a width. So 0.4, 0.8, 1.2, and 1.6. We still want this area here. But now we're going to go up at the left side of this rectangle. So here's the bottom of this rectangle. The left side of it is up here. So notice this rectangle is a little bit above the curve. Same with this next one. We go up here from the left side and then down. It's above the curve. We're getting extra area. Didn't draw this one so well. That's okay. And then this last one here, voila, like that. So now if we want to think about these, we could say this goes from 0 because we start right at the beginning. We don't actually go over first. And we'd go 0, if we went to 5, that'd be 6. So 0 to 4. And we'd have f of, again, 0.4 times I. So that would start us at 0. And then if we plugged in 1, we'd be at 0.4. Plugged in 2, we'd be at 0.8, and so on. And also times a 0.4. This one is going to get all this little extra area from each one. So this one is going to be an overestimate. So we're getting more area than we actually need. All right, but between the two of them, if we kind of like average them or something, we get even closer. And that actually gives us something called the Trapezoid Rule, which we'll look at later. All right, so you will be expected to actually evaluate this on your homework. So you'll be expected to plug this in up here, get a number, multiply it by 0.4, and then add all of them up. All right, so one more practice here. This one might be a little bit easier. So we're going from the curve x squared, the x-axis. We're going from 1 to 3, and we're using 4 rectangles this time. So it should be a little easier to do the sections here. So here's the graph of x squared. And let's say maybe that's 1, that's 2, and that's 3. And we want to use right end rectangles, and we're breaking it up into 4. So if we're going to break it up into 4, the way we find out how long each one is we find the length and divide it by 4. So that's 2 over 4, or in other words, each one is a half or 0.5. So we're going from 1 to 1.5, 1.5 to 2, 2 to 2.5, and 2.5 to 3. All right, so now the right end rectangles, we'd go, here's our first rectangle, we'd go to the right side, go over and down, the right side, over and down, over and down, over and down. All right, so it looks like this is going to be an overestimate because we get this extra area here. And let's see, this would be the sum, so this would be, we'll just do it this way. 1.5 squared is the height here, times 0.5. The height here would be 2 squared times 0.5. The next one would be 2.5 squared times 0.5. And the last one would be 3 squared times 0.5. And then we'd want to work all this out and see what this works out to. And that would be our area under the curve, our guess at it anyways. If we go from the other rectangles, so now we'd start from 1 and go over, 1.5 and over, that and over, that and over. So this will be an underestimate. You can kind of get it from the concavity of the curve and if it's increasing and decreasing. All right, so we're plugging in 1 here and then 1.5 here and so on. So we'd have 1 squared times the width of that rectangle plus 1.5 squared times the width of this rectangle, which is again 0.5, plus, and then this would be 2 squared times the width of that rectangle, which is another 0.5, and then this last one has a height, we'd plug in 2.5, so we'd have 2.5 squared times a 0.5. All right, and that would get us our answer. For this side, we'd have to work this out and throw it in our calculator, but I'll save you the time here. All right, so that is how we find areas under the curve using rectangles and summation. The next one, we'll bring this together and say, how is this related to integrals?